Okay. So by the way, so I hope as of now you have all read my announcement on the midterm examination, which I uploaded in PRMS. So if you haven't, please do it now. The exam is on next Monday from 6 to 9. So although the POVI says the exam is from 6 to 10, but not 10. So it's from 6 to 9 in the auditorium. So you can't miss it. And I will see you then. So this, by the way, this is the last, what I'm going to teach you today is the last topic that will be covered in the midterm examination. So last time we talked about the QR factorization. So what is the QR factorization? Suppose that I have a matrix A. This is an n by k matrix, and this is usually a narrow matrix. So n is greater than or equals to k. And if suppose this guy has linearly independent columns, then we can factorize the matrix as a product of the matrix Q times matrix R. And what is this? This is an n by k matrix, and whose columns are also normal vectors. And this R is k by k matrix. This is upper triangular. And non-singular matrix or invertible matrix. So we have such a nice decomposition. There is a few remarks on the projection map. So, well, suppose that I have my matrix as a QR factorization, then there is very interesting thing happens. Then the normal equation can be reduced to a much easier equation. Well, a normal equation can be written as A times AX is A times, sorry, not A transpose times B. So this is the normal equation, right? But, so if I replace every single A from the normal equation by Q times R, then I have QR transpose QR, I should say X hat, sorry, is QR transpose and B. So this is R transpose, Q transpose, Q R X hat is R transpose, Q transpose, and B. And well, even though this is usually not a square matrix, but however, this is a narrow matrix, but however, if you multiply by its own transpose, then multiplying these two, they cancel, and it's going to be the identity matrix, K by K identity matrix, right? So I can simply ignore them. So this is the ID. And also, I told you that the matrix R, which is upper triangular and invertible matrix. So you're safe to just take the inverse of this matrix. So therefore, you have Q transpose and B. So this is your new normal equation. So provided that you have a QR factorization of the matrix A. Okay. And the next, the projection is also easier. Do you remember the projection matrix was given by? So this is the projection from the n-dimensional Euclidean space to the column space of A. So this is A times A transpose A inverse and A transpose. This was the projection matrix, but again, I am replacing with A by QR, and so this is R transpose, Q transpose, and QR. Everything inverse, and R transpose and Q transpose. Okay. But again, same thing. So this is identity. So, and the transpose and inverse, they are commutative. So I will just simply say this is R inverse times R transpose inverse. I will just simply say R to the negative T. And RT, QT. Okay, and these are inverses to each other. So this is just QT. Q, QT. Done. Okay. So transpose matrix, the projection matrix is also easy. Okay. All right. So for today's remaining lecture, we'll talk about the applications of the function space. So last time we talked about the Fourier series. So what was the Fourier series? Fourier series was actually nothing but writing down any given function. So suppose that f is a function defined on -pi to +pi, and Fourier series was actually turns out to be nothing but writing down that function as a linear combinations of the orthogonal vectors. These orthogonal vectors were the trig functions, sine and cosine, right? So we remember the Fourier series. The Fourier series was okay. So this is a Fourier series. This H means the space of all continuous functions from -pi to +pi, and then for any f, so we were able to write this guy as a linear combinations of function. This is coefficients. This number can be considered as a coefficient of the constant function, and these are the coefficient of these vectors. So this was basically the Fourier transformation. Sorry, Fourier series. Okay, we have the Fourier series, but in practice, well, we are human beings and we cannot deal with the infinities. So, and since this summation contains infinities, so we have to actually somehow to truncate this infinite sum into the finite sum. So maybe like this. I'm going to define a new function, but not completely different. But this time, this sum is not infinite, but this is finite sum. It ends at k equals to n. Okay, so as of now, for me, this looks just nothing but just merely truncation. Okay, truncate this infinite sum to the finite sum. But what I'm going to show you today is this is not just a merely truncation. This is actually a projection. Projection on what? So now things are getting interesting. So we have to remember that this is a vector space, and also this space is equipped with the inner product. Do you remember the inner product? So what was the inner product of two functions? You multiply two functions and you integrate the product from minus pi to plus pi. Then that satisfies all those three axioms of the inner product. All right. And so this is a vector space with inner product. And whenever your vector space has an inner product, then you can always define a projection. Now, under what sense am I claiming this is a projection? I have a vector space V, and this guy is spanned by cosine x, sine x, and cosine 2x, sine 2x, cosine nx, sine nx. This is clearly a subspace. Okay. But there is a big difference. This was, the number of bases. Last time we talked about the orthogonal basis of this system. So the number of basis vectors were infinitely many. So this is I say this is an infinite dimensional vector space. But on the contrary, so what about this guy? So there are only finitely many basis vectors for this space. Okay, so I guess this is a finite dimensional vector space. This is finite dimensional subspace contained in infinite dimensional vector space. Okay. Now, what I want to do is this. Very simple. Choose any vector from the vector space H, and I want to take the projection of that vector, the projection of that function, onto this finite dimensional vector space. Then what do you think will happen? I will call this is a projection map so this is a projection map from H to B. Then for any function f, the projection can be written as, so once you project this guy, then this is now a member of this vector space, which is a finite dimensional. So this guy can be written as a linear combinations of these basis vector. So I will say A1 cosine x, B1 sine x, an cosine x plus bn sine x. And all I want to do is I want to determine each of these coefficients. How? How can I determine them? This is very simple. The idea is I want to subtract this is my original vector, and I am subtracting every single component that belongs to V from my original vector F. Then this remaining thing, the remaining vector must be orthogonal to every basis vectors of this vector space V. Why? Because the V component of F has been removed from V. V component of F has been removed from F, right? Therefore, this remaining component must be orthogonal to each of these basis vectors. Right? This is the idea. Yeah. 아, 죄송합니다. Sorry. Okay. So this guy must be orthogonal to cosine kx and sine kx. So here, so k is from 0 to n, and this k is from 1 to n. Okay. So they must be true. And but this orthogonality condition can be paraphrased by using the inner product. How? F minus the projection and inner product with cosine kx must be 0. And this guy also must be 0. Okay, so so however, the inner product was linear, so f cosine kx is the same as the projection inner product with cosine and is okay, but these numbers are very easy to compute. Not easy to compute, but these numbers are well defined. This is fx times cosine kx dx. And what is this number? Okay, let me say I am replacing this this thing by this huge expression. Then because of the orthogonality of each of these basis vectors, so this must be just simply ak times cosine kx, and you know what it is. So this is time ak times, so this ak times cosine x comma cosine x, but you know, cosine square, the integration of cosine square from minus pi to plus pi is the pi, which is pi, right? So this is just pi times ak, and likewise, this is bk sine kx, and pi times bk. And of course, this is minus pi to plus pi fx sine kx dx. All right, so therefore, we can determine these coefficients from a0 to an, from b1 to bn. So, well, so we are actually repeating the same thing, but however, so this implies this entire discussion tells us, so, the truncation of this infinite series into this finite series is actually implies you are projecting this guy onto the finite dimensional vector subspace spanned by these basis vectors. Okay, so this truncation is indeed a projection. All right. Just one more thing to add. Consider a number. Well, V is a subspace of H, and let us consider this number. So this is what? This is just simply the f minus g squared integral from minus pi to plus pi. This is very simple number, well-defined number. And whenever I change by vector g from the subspace V, then this number will also change, right? Then the question is, so for which function g this number minimizes? Do you know the answer? Yeah, right, exactly. This number is minimized exactly when G is the projection of F onto the subspace V. So I want to tell you, so I want to put on little emphasis on this number. So what is this number? So this number actually implies, this number actually means the area squared. So suppose that you have two functions, f and g. And f minus g squared means, well, it's somehow related to the area enclosed by these two functions between minus pi to plus pi. And this number is being minimized. So the projection of f onto vector space G, V, means that projection is actually minimizing that the discrepancies between these two functions. Okay. In this sense, we say the function is a least square solution of the function in this function space. Okay. Okay. Yeah. Oh, sure. Sorry. I have to mention that this is a subspace of H. Yeah. So actually, F and G, they belong to the same space H. So yeah, we can. So there is the inner product. Thank you. All right. Now I'm gonna make things a little bit more tricky, but idea is almost the same. Another application. This time, H is a space of all continuous functions on, say, -1 to +1. And this space also has an inner product. And this number is defined by the integral of f times g from -1 to +1. So this is a space with inner product. And in this case, this time, I want to consider a subspace of H spanned by all polynomials whose degrees are less than or equals to n-1. this is a subspace of H. Okay. The question is, this time, so what is the sorry. So now what I want to do is very simple, but very similar to the previous exercise, previous application. So for any chosen function or vector from this space H, I want to take a projection of that function onto this subspace. Okay. So this is a projection map from H to V, which is projection. Then for any F, projection of F onto the subspace V can be written as a linear combination of these basis vectors. C n x n minus 1. And also this time also I want to determine all of these coefficients. So what are these coefficients? So idea is the same. So F minus the projection must be perpendicular to each of these basis vectors. So in other words, their inner product must be 0. So solving this is f comma xi minus 1 is the inner product of the projection so I have n such equations. Wait. Now what I want to do is I want to replace this projection by this expression. Then like this. Oh, but so now things are getting slightly trickier than previous case, the Fourier series case. Okay, what makes this one trickier? Well, when in the case of the Fourier series, our basis function, our basis vectors were the orthogonal vectors, right? So which were the sines and sine kx and cosine kx's, right? So when the number k difference, then if two, so that means if you take an inner product of two different basis vectors, then it's going to be 0 automatically. But in this case, this basis vector taken inner product with, let's say, that basis vector is not going to be 0. Right? Because this is our inner product. So, okay, for example, suppose that I am taking inner product with this basis vector with that basis vector. Then 1 times x minus 1 integral, or the integral of x to the minus 1 from minus 1 to plus 1 is not going to be 0, right? Yeah, sometimes it can be 0, but in general, they cannot be 0, right? So we don't have such a nice luxury of the orthogonality. So therefore, I have to solve. I should say k from 1 to n, ck xk minus 1 and xi minus 1. So, okay, so I have this relation from I1 to n. Yeah, I know. So these numbers look a little bit scary, but they are just simply all these. They are all just numbers. These are all computable numbers. Do you think you can compute this number? Yeah, absolutely. These are just high school. This is nothing but high school calculus. So you multiply these two functions and take an integral from minus to 1 to plus 1. Then you get this number. And the same thing is true for that number. Well, this f might be a little bit tricky, but well, this is the computation of this number is also doable, right? So you multiply f by x to the I minus 1, and you take an integral from minus 1 to plus 1, then you get that number. So all these things, they are just a bunch of numbers. So, and since I have n such equations, and these numbers, these coefficients, ck's, they are the numbers, they are precisely the numbers that we are looking for. So I should say this is a n unknowns and n equation system for coefficient C1 to Ck, for C1 to Cn. So let me try to explain in this way. So, well, suppose that my I equals to 1. Then if I is 1, then this is just 1, the constant function 1. Okay. And from k, the index k is varying from 1 to n. So I should say 1, 1, and x, 1, and x squared, 1, and x n minus 1, 1, and C1, C2, Cn is right? This is precisely the equation when I equals to 1. Okay. Okay, all right. Okay, now I can do the same thing for I equals to 2 to n. So if I is 2, then 1 x, 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 x squared, x, x n minus 1, x, and fx. So this is the equation when I is 2, and So x n, So 1, x n minus 1, x n minus 1, x n minus 1, x n minus 1. And Cn, this is f x n minus 1. So yeah, I have some now I have a mystery matrix equation, but this is not actually mystery at all. This is just simply a n by n system of linear equations. And once you solve this equation for this column vector C, then that means you have determined these coefficients. That also implies that you found the projection of F onto the subspace of B. Okay. This matrix is called the Hilbert matrix. So I have an interesting example. that I have found from our textbook. Exercise goes like this. Sorry. I have a vector space H, which is a space of all continuous functions on 0 to, not -1 to +1, but 0 to 1. So in this case, the inner product must be integral not from -1 to 1, but from 0 to 1. So defining such an inner product makes no problem, right? Because it satisfies all three axioms for the inner product. So this is commutative. So you can exchange you can swap F and G, and also this is linear, and the only, and F times F comma F is always positive, and F comma F equals to 0 if and only if F equals to 0, right? Zero function. So this is an inner product, right? Now for this inner product, approximate function fx equals to x to the 5th by a linear polynomial c plus dx, so that the number so I am looking for a linear polynomial such that this discrepancy is minimized. Can I find such a function? Can I find such a linear polynomial? Well, let me try to find such a linear polynomial c plus dx. So, although I have spelled out many cases, so many statements, many sentences, but if you're paying attention to my lecture, then I guess you can easily realize this question is actually looking for the projection of this function onto the subspace spanned by all linear polynomials. All right. If I can find such a projection of the function f, then that projection minimizes this discrepancy, the difference between these two. Okay. Okay. So therefore, the solution is I am supposed to find V is a space spanned by constant functions and the degree 1 polynomial. Then the linear polynomial that we are looking for is the projection of this x to the 5th function onto the subspace. And to find such a function, I need to solve this equation 1, 1. Hold on, I forgot. Yeah. x1, 1x, and xx. Yeah.
The number, there's a variable in there that they have x, so what are we minimizing?
Oh, so sorry. So the variable here is c and d, not x. Oh, because yes. Thank you for pointing this out. Yeah, I have to clarify this. So this is actually fx minus c plus dx, everything squared dx. So so this is an inner product, right? So once you integrate this in terms of x, then the variable exponential. So this is just merely a function depending only on the parameters C and D. Okay. Right. Thank you. Thank you for your clarification. Okay. So C, D, am I doing right? Yeah, and the right-hand side should be F1 and Fx. Okay, so I am supposed to solve this system of equations. And I believe I must be able to evaluate all these entries. So what is this number? This number is 1 integral of 1 times 1 from 0 to 1. Okay, so this is just 1. Okay. What about this? This is the integral of x from 0 to 1. And that is going to be just 1 over 2. And this is again 1 over 2. And this last entry is the integral of x squared from 0 to 1. So which is 1/3. And CD. What about the right-hand side? F is x to the 5th. So this is the integral of x to the 5th from 0 to 1. So this number has to be 1 over 6. And this one has to be 1 over 7. 1 over 7. And solving this, I have C and D is, after tedious computation, it turned out C was minus 4 over 21, and D is plus 5 over 7. Okay. All right. Maybe this is the right time to use the graphing calculator. Oh, okay. So good. So I have drawn the graph of two functions. The first one, the black one, is represent the function of y equals to x to the 5th from 0 to 1. And the red line is the line that we have just found. The linear polynomial from -1 to 1. And as you can see from this picture, so you can easily imagine the area enclosed by these two graphs. So this area plus that area plus that area, right? Actually, the area is squared, but you know what I mean. Okay. And choosing, this black line, the y equals x to the 5th has to be fixed, but this red line is the line that minimizes the area square enclosed by these two graphs. Okay. So in this sense, I say this is the best approximating linear polynomial of x to the 5th. Okay. All right. Okay. All right. What now? Okay, just one last thing that I need to emphasize is, well, this Hilbert matrix is so useful. So especially if you want to project any function onto some space of polynomials. Well, usually the function f should be very much like, so function f is, well, at least to say function f is not easy to compute. Usually function f is most likely function f is a transcendental function. The transcendental function is a function. Well, usually when you try to evaluate any transcendental functions, then it requires a huge effort, time and effort to evaluate the function value. So why don't you approximate the function f by some very nice linear polynomial? If you approximate the function f by some linear polynomial, then some evaluation of the function is like matter of the taking the addition, subtraction, and division and multiplication. But so it sounds like Hilbert. So it sounds like Hilbert matrix is very nice, very nice and useful in practical application. But actually, it turns out it isn't. Why? The problem happens when the size of n is getting large. So suppose that you want a project, you have some function f, and you suppose that you want to project that f onto a space of all polynomials of degree less than equals to 10. Then in that case, the size of Hilbert matrix is going to be 11 by 11 matrix. Well, so when the dimension of the matrix is getting that large, then usually taking inverse matrix to solve this equation is not meaningful. So in that case, in such cases, you have to use the Gaussian elimination, the forward elimination. So Gaussian elimination, I mean, so by applying the bunch of elementary row operations, and you are supposed to transform this Hilbert matrix into the upper triangular matrix. But it has been shown that in that case, the last diagonal entry is very close to 0, always, for the Hilbert matrix. So why that makes trouble? That causes trouble because if this number is very close to 0, then in order to obtain the number Cn, then you have to divide both sides of this last equation by a number which is very close to 0. And that causes problem because in that case, even though your error in this number is very small, the error in this number is very small, but since this number is very close to 0, the small error of this number causes a huge error in this number Cn. And if the Cn has a huge error, then the error propagates to Cn minus 1 and Cn minus 2, da, da, da. So this entire system is very prone to error. Tiny little error in this side will cause a huge error for the solution. So usually, because of the reason, so we usually avoid using the Hilbert matrix. Then what is the solution? The solution is very simple. The Hilbert matrix is not that great because we are using this naive basis. So the choice of this basis vector for this vector space, this subspace, is very easy, but actually, in terms of computation, this is not great because it doesn't enjoy the luxury of orthogonality. So in order to avoid using the Hilbert matrix, well, this time around, instead of using these basis vectors, but we want to make another basis that spans the same vector space, but has the orthogonality. In order to find such a nice basis for this vector space, then we have to apply the Gram-Schmidt process for the space of functions. Okay, so so again, I changed my mind. Sorry. This is a space of all continuous functions on -1 to 1. And the inner product is, as always, the integral of f times g from -1 to 1. And for simplicity, V is span of 1x and x squared. This is obviously the subspace of vector space H. What I want to do is simple. So I want to apply the Gram-Schmidt algorithm onto these three basis vectors, and I will make a new orthogonal basis. So, oh, sorry. What is my Q1? Q1 is just simply normalizing basis vector 1. Okay. What do you think is the length of this basis? What do you think of this length of this vector? This is that one. Why? Yeah, this is somehow counterintuitive, but so this number is very easy to compute because this is, well, it turns out this is -1 to 1, 1 times 1 dx, and everything square root. Okay. And what is this number? So this is, you're integrating a constant function 1 from -1 to 1. So this is going to be 2. So length of this guy is not 1, actually. So length of this guy is square root of 2. Okay. All right. So this is your first orthonormal basis. And what about Q2? Q2 is obtained by normalizing normalizing x, and I have to subtract Q1 component of x from x. So what is Q1 component? So 1 over square root of 2 comma x, and yeah, okay, yeah, okay, right, this is it. Oh, sorry, I messed up. So I forgot to multiply by Q1. Okay, good. All right. So first of all, I have to compute this number. Oh, wait. This number is nothing but 0. Why? Did you see? So 1 over square root of 2 times x is now being integrated from -1 to +1. So this is clearly 0 because this is an odd function. So this guy equals to 0. So it turns out I have to normalize just this single vector x, and this is the integral of x times x, and taking square root. What is this? This is x squared. So 1/3 times x cubed. Maybe. So sorry, my brain is not working. Yeah. Okay, good. So this is my Q2, and Q3 is I have to normalize x squared now, and this is Q1 component of x1. It's Q1 component of x squared, and minus, and this is Q2 component of x squared okay, all right. Yeah, I know this computation is getting annoying, but by the same reason, this x times x squared, this is an odd function from -1 to +1. So this guy just is equal to 0. So the last term, we can simply ignore the last term because they are all equal to 0. So after you spend a bunch of time and effort computing this, it turns out is 8/45 times x squared minus 1/3. So I have these three vectors. These are orthonormal basis for the subspace V. If you just simply ignore all these constants that appears in front of these vectors, then, well, we actually gave the name for these polynomials. So polynomial 1, x, and x squared minus 1/3. So they are not orthonormal base vectors, but they are orthogonal vectors, right? And these orthogonal vectors, well, they are so useful, so we gave the name for these vectors. They are called the so-called the Legendre polynomial, which appears in the quantum physics. Okay, all right. So they are obtained in this way. So the point is that I'm not the expert in quantum physics, but what I want to say is that instead of using just regular naive bases, but why don't you use these bases? Well, they are somehow to obtain these vectors, it requires a little bit of computation, but once you obtain these orthogonal bases, then, well, you do not need to deal with the Hilbert matrix. You can actually deal with very nice and diagonal matrix to find numbers from C1 to Cn. Okay. All right. So I guess this is the last topic that will be covered in our midterm. And I believe this is the right time to finish today's lecture. And I will see you on Monday on the auditorium. Okay. All right. See you then. Bye.